All right, so solutions are homogeneous or homogeneous, however way you want to say that. That's a word we learned in chapter 2, wasn't it? It means all the same. They're mixtures of two or more pure substances. Now, chapter 13 also has vocabulary on it, and I put that on Quizlet today. Do you want another vocab quiz?
Yes.
Okay, it will help your grades. Yeah, the average was like 97.
How much?
Pizza? Nope. That's a one with two zeros behind it.
Like assessment points or like what do you
I don't know. I'll pray about it. Something that doesn't help you very much.
20 assessment points?
Just kidding. I don't know. I don't. Not when money's on the line. Okay. So, sure. All right, you can go ahead and look at those. They're on Quizlet. Um, on Canvas, you can find them at the bottom of the chapter 13 module. Okay, moving on. A solution, in a solution, the solute is dispersed uniformly throughout. That makes sense because homogeneous means it's all uniform. It's all the same. All right, solutions don't just mean liquids mixed together. All right, so whatever. So we have gas, and air is a solution. It has oxygen, it has nitrogen, it has a few other things, carbon dioxide, things like that. All right, we can have liquid, liquid, gas, liquid, 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 solid, gas, solid, solid, liquid, solid, solid, solid. So like, there's all sorts of combinations of solutions. All right, so what's that? Yeah, technically. Weird, huh?
I think that could be a wrap.
It probably could be a wrap. Yes.
If you have like the silver and gold alloy, is it the silver dissolved in gold or dissolved in silver?
You would this well, have we talked about solute and solvent before? Okay. The solute is always the lower concentration. The solvent is always the higher concentration. So it could be either way around. We would just need to know how much we had. So if we called it gold, then gold would be the solvent and the silver alloy would be, or the silver atoms would be in lower, the solute. Go ahead.
So if you have like salt in water and it's like just high concentration, you technically water be the solute.
Yeah, if I took a cup full of solid salt and add a little bit of water, then it'd reverse what we normally would think about. It is weird. All right. Hey, look at that. That was already there. So in order to get something to dissolve or make a solution, the intermolecular forces between the solute and solvent particles must be strong enough to compete with those between solute particles and those between solvent particles. Okay, that's a lot of words. But it's just saying in order for something to actually dissolve, it has to be more attracted to the solute than it is to itself. So, and then it doesn't have to be just like a one-to-one ratio though. It's like water, the power there is it takes a few water particles to attract and separate it. All right, so anyway, when we talk about an ion or an ionic substance dissolving, we're really also talking about dissociation. So that would be sodium chloride. If we ever talk about something nonpolar, it is not breaking into its parts, it's just separating into smaller parts. So this is tricky, but the intermolecular attraction between the chloride ion and water is strong enough to actually break the molecule itself apart. All right, but what's that?
What is that called when it breaks apart?
Dissociation. All right, but sugar, the actual C, H, and O, its attraction to water is basically zero. But two sugar molecules the attraction of the actual whole molecule to water is greater than the attraction to another sugar particle. It's really big. It does have some London dispersion forces that make it attractive to this. All right, now, how does a solution form? You should read this section. All right, as a solution forms, the solvent pulls solute particles apart and surrounds them or solvates them. So you can see, let's see if this is a whole, I can make this bigger. The AP tests, they find it really important that you can draw like representations of solutions. So these pictures, they're not super hard, but be familiar and able to draw them. So what we have is we have our solute, we put it in water, and it starts to be attracted. There's an attractive force here, and it starts to break apart. All right, or the water solvates the solute. That crystal gets smaller and smaller, and it becomes all broken apart. Once it becomes all broken apart, just the kinetic energy of the system will cause it to disperse evenly, and then we call it a homogeneous solution. Yes.
So like putting like a solvent or a solute in water, would that like make the water more viscous?
Slightly, yeah. It can. I gotta be careful there, because if you put a non-polar solvent in water, it doesn't really mix, like it doesn't solvate, but it can break like sugar. It can break apart, and some of those will actually make it less viscous. So there's not a 100% guarantee that happens. All right. If an ionic salt is soluble in water, it is because the ion dipole interactions are strong enough to overcome the lattice energy of the salt crystal. This is an important thing that they usually will ask you.
Wait, so are most ion dipole interactions stronger than lattice energy?
Yep. You got it. Hold on. You got, so push it in there just slightly and then lift the tip. More than that. Oh, no, not that hard. Now tip it up and then spin the pencil. That's down. Oh, there you go. There we go. Should be good to go. Because it's broken. Okay, I'll read it and draw at the same time. If Na and Cl dissolve in water, it's because the attraction between Na, the ion, and water, the dipole, is stronger than the lattice energy that kept Na and Cl stuck together.
Oh, because is it dissolve? Yeah, it's dissolve actually means, right? Is when they pretty much just get attacked by the water molecules.
Pretty much. Now this is for ionic substances. Okay, slightly different for polar and non-polar substances. And you'll notice, look, you can see it's a 1, 2, 3, 4, 5, 6 to 1 ratio. So honestly, the Na and the Cl hold on pretty tight, and one single water molecule could not separate them. But when you get 6 here and 6 here pulling opposite ways, then it definitely can pull apart.
On the sodium, there'd be 12 total dipoles. Because the oxygen has two. It's just like 2 sigma right there on the oxygen.
Okay. Yeah, so I wouldn't say it has 12 dipoles, but I would say it's 12 strong, so to say. It's still 6 of them, but yeah, since both of the electrons have moved up here, it is a double whatever, and usually you'll never see a 2. It'll just put the minus in the plus, but yep. Okay, now some things are not soluble. We will learn that. We have learned that actually in chapter 4. Do you remember that? So, yeah, the solubility stuff. So, silver chloride is not soluble in water. And that's because the lattice energy between these two is stronger. Okay. Nisha, question? Okay, that's all right. And then you might remember we always used AgNO3 in our examples as something that did dissociate. All right. And then we react it with like chlorine to make something that did not dissociate. So this, the lattice energy here was weaker. The lattice energy here was stronger.
So this is why like precipitates for
Yep, a precipitate forms when the two ions' lattice energy is greater than the ion dipole interaction. Yep, it's when two things react to form a solid. So Ag was an ion in a solution. We had NO3, which we're going to remember say it's a spectator ion. And remember, this is always soluble, right? So what we're really learning is NO3 in any lattice is always more attracted to water than its other partner. Okay, but then we put it in the presence of like hydrochloric acid, so like H plus and Cl minus. And these two, when they came by each other, they thought, we're going to hang out. I would rather hang out with you than water. So we ended up with AgCl as my precipitate, and I ended up with these two things as my spectator ions. Yes, sir.
so nitrate it dissociates easier because it's like a bigger molecule. It's easier for water to.
It's definitely easier for water to solvate it. It's not always, well, that shouldn't have drawn. It's not always because of size, because there are other things that aren't, but size definitely does matter. So C2H3O2 acetate is always also soluble, no matter who it's with. All right, here we go. Energy changes in solution. This is one time where this is not taught as much in this class as it is in regular chemistry. So here we go. Simply put, three processes affect the energetics of the dissolving process, or delta H. Remember, that's what we use when we talk energy. So first, the separation of the solute particles. So literally, as my solid starts to break apart, there is some energy involved. All right. The separation of solvent particles. If you think about it, in order for this to fit in, everything around it, I should do that in a different color. The solute, which we'll put as red, it literally had to separate to make room for that blue to move in, if you think about it that way. All right, and then we have a new interaction between the solute and the solvent. So these two things right here are endothermic processes. The last one is exo. So it always takes energy to split these apart. Now, that doesn't mean I have to heat it. It can get that energy from just the temperature of the water. All right. Some I have to heat, but typically, if I put something in that's going to dissolve, it just starts to break apart, and we call that part endothermic. If it's endothermic, it means that this process would always make the solution cooler. Okay, then this step is also endothermic, where the solvent has to spread apart to make room. All right, but then the last part, the attraction between these two, that is always exothermic. So these two make it cooler. This one makes it warmer. And here's the deal. There's math involved that we don't have to do. We do not have to do the math. But the combination of these three things will tell us if the overall process is endo or exothermic. Because when I put salt in water, it cools the water. Now, you might think, well, why does it melt? But that's a completely different story for what we will learn about that in a minute. Well, in a day. But technically, putting salt in water causes its temperature to go down a little. Now, almost nothing for salt.
I feel like though, we feel like the opposite because we're adding stuff that we should like add more pressure, which would make them,
No, pressure
because wouldn't there be more taking?
pressure has something to do with it, but adding something does not change the pressure. It changes the vapor pressure, but that doesn't change the temperature.
Then why does putting salt on a snowy sidewalk melt it?
Okay, that when I said that's a different story, um, it's a colligative property, which we'll talk about. And technically, no one, hold on. And everyone believes it how she just said it. Salt does not melt ice. Period. It does not melt ice. Salt prevents ice from being formed. So what happens, and we'll talk about it because it's actually part of this chapter. Because if I go out today, let's see, it's 28 degrees and I put salt on ice, it's just going to sit there. But if I'm worried about salt forming, or sorry, ice forming, I put salt down and salt water freezes at a lower temperature than pure water. Salt water freezes at 23 degrees Celsius instead of 32.
Oh, you meant Fahrenheit.
Yeah, this is Fahrenheit because that's what we're used to in our lives. So, and it's, once again, we'll get there, but this is a colligative property and it has to do with the amount of salt we put on the road. Now, the last storm, what's that? Yeah, it gets in the way and stops them from forming it. All right, now, for real, give me time. We'll talk a lot about this. But you may have noticed the other day, like we had rain, but then we had a little snow, maybe Sunday. I can't remember. But if you drove around then, they didn't put salt down, they put dirt down. In Brigham, they did. They didn't even notice that. Why'd they put dirt? Because it was colder than 23 degrees. There's no point in putting salt if you're already below the freezing point of where ice would be formed. So they put dirt and sand just down for traction.
It could actually be worse if they put salt out and it was really, really.
It's not worse, it's just completely pointless. So in Idaho and Montana,
They use lava rock.
yeah, they crush lava rock. They don't put salt. It's pointless. It's too cold.
We used to get things in lava rock when I used to live there because my dad would always say if there's no point in putting salt down because it's just gonna freeze anyway. It's too cold.
Right. Once you're below 23, it's pointless. Okay. So now there are things out there, they're called ice melters, and they're usually blue. Ice melters are a solution, or sorry, a substance that is exothermic as it dissolves.
So it reacts.
So it doesn't react, be careful. As it dissolves, if it can have any bit of moisture, it will start dissolving and that will produce heat, which melts the ice, which gives you more liquid, which means it dissolves more and gives off more heat. What's in it? Copper sulfates. And there's tons of different ones, but that's the most common one.
Is it because it's easier to break apart than normal ice? I mean,
Well, the ice melter, the reason they choose what they choose is because they need it exo and they need it not to kill animals or plants. So they put things on there that are pretty harmless. Okay, we got to go on. All right, but just realize the balance of these will tell us whether something's endo or exothermic. All right, now I'm going to skip that for now. We've talked about system and surroundings in a different chapter, right? Okay. So the system, as we're talking now, refers to the solute. The surroundings, we'll talk about the solution.
Before we just had surroundings and everything else.
Right. And it really is everything else. But if we're going to discuss these things, we would need to know what we're talking about. The system, that's when it's actually dissolving. And the surroundings, we're talking about how it dissolves, what it does to the solution. And if we're talking about energetics, we're talking about whether the surroundings temperature goes up, and that would mean the system was exo, or the temperature goes down, and that would mean the system was endo. So you have to understand that we describe this, but we describe it based on that observation. It's a little bit weird, but we've talked about this in chapter 5, so I'm not going to spend too much time. That's why I skipped those previous slides. All right, so the enthalpy change, or delta H, of an overall process depends on delta H for each of these 3 steps. And once again, it's math, but we don't have to do that math. So why do endothermic processes occur then? Seems kind of like an odd question, but things don't typically occur spontaneously or without outside intervention unless the energy of the system is lower. But that's not what happens when an endothermic process happens. We're actually gaining energy. So it has to do with yet, hold on, where's the word I'm looking for? It's coming up. Okay, sorry. Anyway, yet we know that in some process like the dissolution of NH4NO3 in water, heat is absorbed, not released. So if I take this powder and put it in water, the temperature of the water decreases because the system took in energy. So enthalpy is only part of the picture. The reason is that increasing the disorder or randomness, known as entropy of a system, tends to lower the energy of the system. Now, entropy, we have a whole nother chapter of that coming up. And it's not something I need you to memorize, but it's just, even though we absorbed energy, going from something that was solid and ordered to something that's now all spread out, the overall change, even if it was endothermic, still gave off an energy loss. So it's the balance of enthalpy and entropy. Don't stress too much about that because we have a whole chapter on entropy coming up on chapter 19.
Is there anything that's really endothermic that'll like drop the temperature by a lot? We have things that are really exothermic.
Yeah, you have them. So this stuff right here, this is the stuff that's inside like a non-ice but athletic cold pack. Like Burgraff, he has them. They sit there at room temperature their whole life in a bag, but then he's so freaking loud. All right. So, oh, well, congratulations. All right. So, he'll have these in his bag. They're just circular things because you're gonna unwrap them, lay them flat, and then snap a little thing in each little compartment. And what happens is you now add liquid to the solid, so dissolving happens. It needs a lot of heat for it to happen. So it removes heat from its environment, or it removes heat from like a wrestler's sprained ankle or something like that. Okay, so it's something you can have that doesn't require you to run to the ice machine and get a bag of ice. We've used them in track plenty of times. Right now, you have probably used the opposite, which is a hand warmer. Now, there's 2 types of hand warmers. This is the kind where you can boil it and reuse it. Does anyone own any of those?
I do.
Okay.
There's like one.
Right. It's this little thing that, if it's like the ones I have, it's a clear liquid in here, and there's a little metal piece right here. And what you do is if you haven't used it before, it's just a liquid. But once you want the heat, you use your thumbs to like snap that piece of metal, and it makes like a concussion. And that causes the liquid to turn into a solid. So the reverse of dissolving, and it gives off heat for like an hour. And you just put that in your pocket and hold on to it. And these are nice because you can reuse them. If it gave heat off to turn to a solid, what do I need to do to make it a liquid again? I just put the heat back in. I boil it for a little bit and then make sure I don't snap the little metal thing, and it will stay a liquid until I'm ready to have a warmer again. They work pretty good. Um, if you treat them right, they can last forever. Now, most hand warmers are not this way. They're only single use hand warmers, like the hot hands, and that's a little bit different chemistry. Hot hands, you have Fe solid, then you open it up. Once you open the seal, now you add oxygen and you make Fe2O3 plus heat. But once this reaction goes that way, it's over. We can heat this all we want and we can't reverse it for other reasons. Okay, I got to move on. We're taking way too long. You guys ask really good questions. All right, so did I already do this? Well, it's pretty much the same. So even though enthalpy may increase, the overall energy of the system can still decrease if the system becomes more disordered.
So when they become less disordered, they release heat, but when they're more disordered, they take heat.
I believe if you said that the way I think you did, then yes. All right, now, student beware. You should know this. This should be a can you pass AP chemistry? Just because a substance disappears when it comes in contact with a solvent doesn't mean a substance dissolved. It could have reacted. Right.
Because it could have.
So, right. I don't remember what's in here. It's probably iron. So if we take concentrated acid and we add iron, a reaction is going to happen and these will disappear. I mean, we've seen this year. It was magnesium when we did it. All right. Now, the reason it's different and what would be obvious is this will produce bubbles typically. And if you see bubbles given off, there wasn't dissolving, there was a chemical reaction. So be careful. Just, I mean, it's not usually tested because it's like super basic chemistry, but just in case, just remember there's dissolving and reaction, and they are different. All right. What? What?
Just that, yeah, just that dissolving and reactions are different.
That's the whole point there.
Okay, I
So,
thought there was like a deeper meaning.
nope.
I was like, oh, I'm confused.
So dissolution is a physical change. A reaction is not. So if you can't reverse the process, it didn't dissolve, it reacted.
Yeah, like the thing, difference between the hot hands and the boiling.
Right.
Yeah.
All right. See if you can answer this question. This is probably not accurate. It might be. I don't know. There's not a ton left.
When do you think the test will be?
Probably Friday. What's today? I don't know. We have math left. I don't know. We'll see. We're out of here in 13 minutes, right?
Low iron.
You died. Yeah, talk about this for 30 seconds. Ready, go.
It's what?
All right. Who says it's A? Who says it's B? C. Good. D and E. Good. There's only one word we've talked about.
That's what I was saying.
All right.
Y'all made me
Yeah.
Wait, are these other things that are like actually?
These are all real things.
Well, I was gonna say, I can't tell if it's the way you write the questions, but like it kind of
I was like, salutation, isn't that the one thing for Mary Poppins?
Could have been. I don't remember.
That's what Sky was doing.
Okay, I'm going fast because you're going to read. Types of solution is saturated. It means it's holding as much as it can. I have no idea what this is, but it's cute.
That's what I treated me.
These are on the matching terms that you will all look. All right, now this is a little interesting thing here. At when something's saturated, dissolved solute is in dynamic equilibrium with solid solute particles. So now what this means is a dynamic equilibrium means nothing changes, but there are things that are changing. So that doesn't make sense except for watch. A dynamic equilibrium at saturation means some of this might dissolve, but if it did, some of it came out of the solution as well.
So it's not overall changing. but
There's
there are
no
some changes.
overall, or we call it a net change.
Yeah.
So there was a change, but not much. Okay, so the example I use in normal chemistry is you're at a dance party and there's only 50 people allowed here. And for some stupid reason, you invited me. So I'm just chilling here at your dance party, looking ornery with my earplugs in. Okay, and then give me someone cool. What's their name?
John Nation. Yeah, John Nation.
John Nation. All right. He would have already been at the party, but let's say he was not here yet. So John shows up and Cooper's holding this party. And John, he knocks on the door and Cooper's like, wow, it's full, but John is super cool. So I'm going to let him in. Well, what has to happen at the back door?
They have to take someone out.
You kick me out. So the vibe at the party has changed, but have the total number of people changed? No, this is a dynamic equilibrium. If one comes in, one goes out. And that's what happens when something is saturated. Okay, next. It's okay. You know what? Usually people say like LeBron James. So you should be honored. Or Channing Tatum.
The only reason we got 50 is COVID.
Yes, I appreciate it. Unsaturated. Well, if you understand English, that means lower than saturated. Under, that means down. Or, well, weird. Unsaturated, it holds less than the maximum amount of solute for that temperature. So, I don't know if you guys have all had cereal like Cheerios. To me, and don't argue, to me, Cheerios are only good if you put sugar on them.
Well,
All right,
what about
so
Honey Nut Cheerios?
I don't eat those. I don't eat Cheerios either. So look, Cheerios are best as long as you add sugar. And the only way to know that you have enough sugar is if you get some on the bottom.
Yeah, I love that.
If there's not some on the bottom, then you probably could add more. Hold on. So unsaturated means there's nothing on the bottom. You can keep adding. Saturated means there must be some on the bottom. All right. And if any of it dissolved, some of it would dissolve or undissolve, come right back. Okay, Cooper first. Go.
Light sugar is really good. Like the cereal light.
Yeah, the big chunky sugar.
Why do you have to talk about, you talk
Yeah.
about life, I swear, every.
Anybody else? Okay. The next one is super saturated, which again, if you understand English, it's okay. Super saturated means it's holding more than it should, or it's above its saturated point. Super saturated are a little tricky. In order to get it to hold more solute than it should, you have to go through this process. You have to take a solution and heat it. And while it's hot, you add as much as you possibly can, like syrup. And then you let it cool completely undisturbed. All right? You don't let it vibrate. You don't put another crystal. You don't do any of that stuff. You let it cool and it will stay in solution.
Oh, is that how you make rock candy?
It's sort of how you make rock candy. And it's sort of how you make those exact hand warmers I was just talking about. Let me find this for you. It's pretty cool. All right, so here we go. This is a solution of sodium acetate, most likely. I can't really see, but I'm sure it is. Um, Now, it is a liquid. You will notice maybe just a little thing, a little crystal, just one or two of them lands on the surface, and then the liquid. Do you see that crystal?
Right, the tip, we're gonna add that to my supersaturated solution of sodium acetate.
I don't know why I muted that. That's all he's going to add.
We will see it go from
And
a
then
supersaturated
the
state.
excess solute has to come out of solution. It can't hold that much at that temperature.
So we see that the sodium and acetate.
No, salt doesn't work very well. You have to have a really unique structure enable for it to stay that supersaturated. We can get a supersaturated salt, but not that well.
So it just like literally became solid.
It literally became a solid and trapped most of the liquid in it.
So now we're back, there's a little bit of
So-
water in there. Maybe a supersaturated state.
Now, by the way, in order to do this, you have to heat it. So what happens when you do the reverse?
Add that to my supersaturated
You don't have to
solution of
cool it,
sodium acetate.
but the heat comes out. So if he were to grab the side of this beaker, it would be very hot.
With his hand.
Well, it's not a beaker, sorry, Florence flask, because Florence has a round bottom.
So we see that the sodium. and
What's that?
acetate ions recognize the crystalline structure.
Yep, this process is exothermic.
Okay, so it
Sorry.
reforms the crystal because.
Yep. So now how could he get this back to a solution? No, heating it again. He'd have to boil it for probably 20, 30 minutes. Okay. Doesn't melt. It looks like it's melting, but it's really dissolving, they are different things. Anyway, kind of cool stuff. So that's super saturated.
Weird how you have to heat it to make it to work, but then you have to heat it again to reverse it.
Reese, hear me out. Okay. Hot tub. Turn the water off. Then it starts cooling down. One of those bad boys. Then you got crystal bath.
That'd be so funny. You just pull from somebody like crystallize them.
Oh, they need a whole brand new hot tub.
That sounds like a-
Okay.
It's completely.
Watch out, David.
Well,
Someone
I wouldn't sink. That's so dense, I would not, no one would be in that. You'd be floating on top. All right, here we go. You may have heard the term likes, dissolve, likes. There are factors that affect solubility.
Like polar.
Polar substances tend to dissolve in polar solvents. You absolutely have to know that. Nonpolar substances tend to dissolve in nonpolar solvents. If you have similar intermolecular forces, you will typically dissolve in each other.
Is there any way to dissolve them with each other or no?
Well, you can temporarily dissolve them by like shaking them. So like you can take your Italian dressing and get them to mix, and you're like, oh, I got them all mixed up. They all dissolved, but just let it sit and they'll come right back out. So long term, no, you can't. You can mix them, but you can't get them to dissolve.
Can things undissolve over time?
Yeah.
Not with this or.
Yeah, usually that happens because the liquid evaporates over time, leaving the solute. All right. Probably not, just household ones. But you can buy sodium acetate probably really cheap. It's very hard to get it to work because usually, like I've tried it in this class, I've got it to work maybe 2 out of 10 times. When it cools, it has to be so carefully undisturbed that it's almost impossible. So you cool it, and half the time you're letting it cool, it just solidifies without that fun dramatic thing. If you remind me at the very start of the class tomorrow, we'll give it a shot and see if it works.
Does it have to be completely cooled before you take
It
it
needs
out?
to cool a lot. Not completely, but it better be pretty close back to room temperature. Okay, here we go. The more similar the intermolecular attractions, the more likely one substance is to be soluble in another. I have no idea, but I don't draw well, but that one's kind of cute. All right. I'm moving on. 5, 4, 3. I was watching Wild Planet and watched like 20 alligators eat a little baby hippo, and it was the saddest moment of my life.
You ever seen the big hippos though? Don't chop a whole alligator. With what?
He was pretty chill. Okay, glucose. That's sugar, right? We know sugar dissolves in water. That's because it has hydrogen bonding. That's weird. So does water. All right, so cyclohexane, which only has dispersion forces, is not. So the size, the length, and the hydrogen bonding are what makes sugar pretty good at
So
dissolving.
there's so
Wait,
many
I'm
different
confused.
things that go into disassociation.
Yep, go ahead, Grace.
So the stronger the intermolecular forces, the more soluble it is in water. That doesn't make sense.
They had to be
No,
They
well,
have to have the same.
the closer, the greater it is, means it moves being more polar.
Okay.
And so that will cause it to be more soluble in things that are polar.
So since
Wait.
both sugar and water have strong intermolecular forces, then